Welcome back. So I'm going to continue the lecture talking about interaction between orbitals and molecular orbital theory as well. And this slide, we see one hydrogen is interacting with another hydrogen, and it is giving us one hydrogen-hydrogen bond or a sigma bond. And the second one is a hydrogen plus another hydrogen, but this hydrogen is coming with at a phase orbital. So technically, the two hydrogens are not in phase. We get the orbital that we call it anti-bonding and show it by sigma star orbital. Okay, so let me sort all this type of orbital interaction that we might get, and I'm going to be talking about them and or drawing them here for you guys. Okay, so okay, first example, let's go with hydrogen. We have hydrogen orbital. Okay, interacting with another hydrogen orbital, and we're going to assume that they are in phase. What does it mean? Well, if this one is positive, the second one is positive as well. Okay, you will say this is one element, and that's a second element. So I'm going to say M1, M2. And if they are in phase, M1, it will be attached to M2, and this is the orbital between them. Okay, we show it by such a thing. And we say they build a sigma orbital, technically, or a sigma interaction. Okay, you're going to put two electrons in it. One is pointing up, and that's the second, and that's the second one. So this is going to be a sigma, and you show it by a single line between the two M's. Okay, so this is a sigma bond. Okay, next, I'm going to take M1 plus M2, but I will change phase of the second one. So imagine second one, this time, the second one is negative. So we change this one to negative. What do we get if one of them is out of phase? Okay, so technically these two are not in phase. And in that case, we say M1 is not attached to M2. There is a node between them. So this is going to be a node. Okay. On one side, you will have, okay, or you can draw it by a circle here. Well, let me change the sign of this one. I'm going to go different color. Okay, one of them is positive while the second one is negative. There is no bond between M1 and M2, and we call this one sigma star. Okay, so the top one was sigma or bonding interaction. Okay, bonding interaction, this is going to be anti-bonding. And because we are talking about the head-to-head interaction, okay, head-to-head interaction, I'm going to call it sigma star. Okay, that means it's anti-bonding. And what did I use? I used S plus S. All the top was sigma. Okay, sigma, and is S plus S. Okay. Now, let's interact the hydrogen or S orbital with a P orbital, okay? So I'm going to say, imagine we have an S orbital and interacting with a P orbital, and this is our P orbital, okay? And of course, I want them to interact head-to-head, so I'm going to draw it this way, okay? I have two possibilities for it. They can be in phase or out of phases. Okay, so let's copy this. I go plus, first one is plus. If this one is plus, that one also plus, minus, this is a plus, and this one is minus and plus. We can highlight them. Okay. Okay. So when I add S orbital or hydrogen orbital, for example, to a P orbital, if the interaction is head-to-head and they are reaching in phase, you will get, okay, you will get interaction between them, and that's going to be a bonding interaction. So this is M1, the first element, that's M2, the second element. So M1, it will be M1, it will be attached to M2 through a sigma interaction. This is a sigma interaction. similar to the previous one. We're going to have 2 electrons in it. One is pointing up, the second one is pointing down, but also we have a tail here. And what will happen with this tail? Okay, that's that one. That's not going to help us with the interaction. So we're going to get this, and I'm going to, again, that one is the negative. Okay, that's not going to help us. The bonding is here. This is the bonding one. And then that one is not helping you, again, not helping you to attach two elements to each other. This is going to be a sigma, okay, sigma interaction between S plus P. Okay, but what if they are atom phases? If they are atom phases, this is going to happen. Okay, you will have M1. Okay, clearly there is a node between them. So you will show that you have a node there. Okay, and then show M2. Okay, this is the first orbital. Okay, first orbital, let's say, and we're going to call it, for example, yellow. Okay, it means here is positive. Okay, this side, I'm going to have one that is negative. That's atom phase. Positive cannot have interaction with a negative one. And where is the positive? Positive is pointing out. Okay, and that's going to be sigma star of SP. Okay, so the top one is bonding again. And this is going to be anti-bonding. Okay, now add P to another P orbital and see what will happen. So I'm going to copy paste those. Or we can actually, yeah, copy. Yeah, let's copy paste everything here. Cool. So I have this one. I'm trying to speed the lecture. Okay. First one, I'm just simply gonna erase the the S orbital, and I will replace it by another P orbital. Okay, this is another P orbital. Okay, positive here, negative there. Okay, and that one I'm gonna flip it. So I go. This is gonna be positive and negative here. Okay, again, this is the yellow. That one is the yellow, and okay. If the positive reaching to the positive, or they are reaching from the right, sign, then your interaction, it will be constructive, or it will be bonding. So that's going to be a head-to-head interaction. Head-to-head interaction, we call it a sigma interaction. And so the difference between like a PP interaction versus SP interaction is that you're going to get another piece here, and that one, it will be negative. Okay, negative, and this interaction, I'm going to call it sigma star of the sigma of PP. Okay, 2p orbital reaching each other head to head, and they were giving you another sigma interaction. Okay, but this time I got 2 areas that they are not helping me with, and bonding. So those 2 are not really helping us. And whenever we're talking about sigma, this is the sigma technically area. That's going to be the sigma area, similar to that one. So I can erase this one as well. Okay, if there are atom phases, and then you just simply erase this and draw p orbital. Let's say I have M1, okay, and I have orbital, it's pointing this direction, another one pointing that direction. This is going to be positive, and that one is negative. And as you see, because we have different, like we have different signs, like positives pointing to the negative, we're not going to have bonding interactions. Okay. And every time I cross the dashed line, I'm changing the sign from positive to negative. So that means I'm dealing with node. That's a node. And again, similar to the previous one, this is node. Okay. And this node, like this interaction, I'm going to call it sigma star of PP. Okay, sigma star of PP. Okay, what will happen if the p orbital reach each other parallel instead of head to head? Okay, so if they are head to head, we call them sigma. But if they reach each other parallel, okay, they can be aligned the same direction, and both like the positive or up and the negative down. That's one possibility. Or flip the second one, and that's another possibility. So if they reach each other parallel, we will have two cases. Okay, so say this one is, okay, 1p orbital, let's call it pz, plus minus. We're going to copy paste this one. Add it to the second. And another case, I'm going to flip them. So now I go, this one is, okay, skip this one. Okay, forgive me. This one is going to be negative. Here it will be positive. Okay. So again, I'm going to highlight positive, positive. This one is positive, and positive is down. Negative, negative, that one is negative here, negative up. Okay, we're dealing with pz orbital. We are adding two pz orbital to each other. So pz, that's another pz orbital. Okay, first case, when they are reaching each other and they are parallel and they are in phase. So what do I get? M1, okay. Okay, M1 is already attached to M2 through what? Through a sigma. You already use one, interaction, whether it's a PP or SP or SS interaction, and you made a sigma interaction, sigma bond between them. Okay, so already we do have sigma. Already these two are connected to each other. I have nothing to do with, it has nothing to do with the p orbital that I'm talking about it, okay? The p orbitals, you have a p orbital here, another p orbital there, that's positive, this one's positive, and you show them by, okay, here, you show that interaction between them by a bunch of dashed line, and then here down, I have negative, negative, the negative also, it can see the negative. The output of this, M1, will be attached to M2 through a sigma bond and a pi bond. Okay, this is going to be the pi bond. So this interaction, it will be pi bonding interaction. And how did I get it? I use 2p orbitals. So I said pi pp interaction. Okay, another case, okay, M1 and 2. Okay, so I have a positive sign here, negative sign there. Okay, there is this one will be negative, and here I have positive. Okay, so let's see. Okay, do I see any node between them? Clearly there is a node. And where is the node? The node is here. Okay. So we have a node there. Okay, because the sign from positive is turning to negative. Okay, so again, here. Okay, so what do I get? Do I get any interaction between them? No, you're not going to see any interaction. The positive will not have interaction with the negative one, and this is going to be anti-bonding orbital. Okay, so in order to show that this is not bonding, we say star. That means anti-bonding, and this is anti-bonding interaction of PP. Okay, is M1 attached to M2? Yeah, you already have one sigma interaction between them. So there is one sigma. Okay, there is sigma. And we're not talking about the sigma. We're talking about the pi interaction. Okay, M1 is not attached to M2 through a pi interaction. It's attached through a sigma. Okay, sigma one. So I got two interaction until now. I got one is pi, and the second is pi star interaction. The pi sometime the pi interaction we show it this way. Okay, so instead of drawing this, we say M1 attached to M2, and we draw a cloud in the top and one at the bottom, and we say this is positive and that one is negative. That means in reality, you're gonna see electron density, constructive or bonding electron density on the top, and one also at the bottom. And this is another representation of pi interaction between 2p orbitals. Okay, and these two are completely equal. Okay, again, I leave it to you which one you prefer to show, but like the one on the right is kind of like an easy or short way to present a pi bond. Okay, and so if I like if I add 2 pi orbital, I can get I can get pi bonding interaction or anti-bonding or an anti-bonding interaction. This is going to be the PP interaction, and that one it will be the pi star or PP interaction. And so the pi orbital by itself, whether it's a bonding or anti-bonding, always is going to have one node. And what's the node and where is it? And so as you see here, there is a plate, or there is something that is changing the sign from positive to the negative. From up is positive, I go down, it turns to negative. So clearly there is a node there. But if I look to the sigma star, I see two nodes. One is perpendicular, and the second node, it will be here. That's going to be there. That one, it will be the second node. And the positive is turning to negative. So one node, it will be here. That's one node. And the second node, it will be in this position. Okay. So pi star has two nodes. Pi bonding, it has only one node. The higher nodes you get, the less useful interaction will be. Okay, the higher node you have, the less useful, or put it this way, that interaction will be weaker interaction, and okay, it might be almost equal to 0. So for pi star, I have two nodes, while for pi, I have only one node. Which one is going to be more useful? Of course, the pi bonding. Okay, now, in general chemistry, you learned that we can mix one S plus another S, or S and plus P, to get one bond. In reality, that one does not happen. In reality, the electron, and as it said, is a cloud. It's distributed over entire of the molecule. When one molecule interacting with another molecule, it's not like one specific atom interacting with another atom. In reality, a cloud of this molecule is sensing another cloud from the second molecule. Okay, we do not pick one atom from another atom and say head to head go and interact with each other. No, that's not going to happen. Okay, what's the electron density and where is it? Okay, so we have a theory that we call it molecular orbital theory, because it says molecular, that means you're dealing with a molecule, and the orbital is distributing over entire of the molecule. The orbital that they are going to do the reaction, they are not atomic orbital, they are molecular orbitals. The highest orbital, we call it, forgive me, the lowest occupied orbital, we call it the HOMO, okay, HOMO orbital, and the highest one, we call it LOMO, and we'll go after them. But let me show you how to get molecular orbital, for example, for H2. Okay, so I'm going to actually present how to get this diagram. Okay, start with this. Okay, simply, please move on. Okay, so start with this. On the top, okay, left side, right, atomic orbital. repeat this one on the right side. Okay, and in the middle, say molecular orbital. Okay, cool. Now we have two hydrogens. Okay, one hydrogen, okay, any hydrogen, it has one s orbital. So one s orbital that it has one electron. Show that electron here. And another one is going to have same level of energy. So as we go up, energy increases. Okay, and we're going to have one s. Okay, that's another hydrogen, and it has one electron in it. Okay, these two are going to reach each other. When they reach each other, they will give you two possibilities. They can be constructive or constructive interference or destructive interference. Okay, if it's constructive interference, that one is going to give you, forgive me, that one is going to give you a bonding interaction. Okay, so we're going to show it by one orbital. Okay, and that orbital, we're going to put two electrons in it, one up, the second one will be pointing down. How did I get this? I interacted, okay, two orbitals head to head. One was S, and the second is another S from hydrogen, another hydrogen atom. This is a sigma interaction, okay, and we call it bonding. Okay, bonding interaction. Orbital that we got it is going to be a molecular orbital. Okay, that's a molecular orbital. The new orbital that you will get, or the second orbital that you will get, will be here. Okay, that's going to be empty. I have only two electrons. I already used them for making bond, and it will be empty. And what's that orbital? This is orbital that will be sigma star of SS. So I use two atomic orbitals, and I got two molecular orbitals. One of them is full, and the second one is empty. Now we have a term that we call it bond order. Or there. Okay, what's a bond order? Bond order is equal to bonding electrons minus anti-bonding electron, and you divide this one by 2. Okay, why by 2? Because per each chemical bond, you need to have 2 electrons. Okay, so I'm going to divide this one by 2 because per each chemical bond, I need to have 2 electrons. Okay, so let's find the bond order for H2. Okay, the bond order for H2 molecule. Okay, so bond order for H2, that's going to be equal to, how many bonding electrons do I have? I have 2 of them. How many anti-bonding? 0. Divide by 2, that's going to be 2 divided by 2, 2 will be 1. So that means hydrogen is attached to another hydrogen through a single bond. Okay, single bond. Okay, so this is going to be a single bond. And single bond always will be sigma bond. Okay, now, can I have, for example, can I have molecule like helium? Okay, so let's go practice this one for helium. So can I have element like molecule like helium? And helium, remember, it has 2 electrons in it. So you're going to say this one, it will be 2 here, and that one is going to be also 2 as well. Okay, can I make He2? Is it possible? Okay, out of those 4 electrons, we're going to use 2 of them for sigma interaction. And now we have 2 more. So what do we do with them? One is pointing up, the second one will be pointing down. Now let's get the bond order. Bond order for He2, it will be, we have 2 bonding or 2 inside sigma, okay? And how about anti-bonding? We have also 2 there, divide by 2, that's going to be 0. What does it mean? It means you cannot have helium attached to another helium. That's not possible, okay? That one is not possible. So how can I get like 2 helium attached to each other? Okay, one way to get it is to remove 1 electron from the system technically. So if I take 1 electron from the system, so again, let's copy paste this. Say you have this. Helium 2 times plus 1. So I'm missing 1 electron. Okay. One of the helium is missing 1 electron. Take electron from one of them. It doesn't matter which one. So let's take 1 electron from the right side. That one, it has only 1. Okay. Means this helium is a plus 1. Okay. And left side is neutral. Now, on the top, I'm going to have only 1 electron because totally I have 3 electrons. So what's going to be the bond order? The bond order, it will be 2 minus 1. That's going to be half. So is it possible to have 2 helium attach each other when there is a positive charge? Yes, that's possible. But remember, this species is going to be unstable, but it's not impossible. It's not impossible to get helium attached to another helium while the total charge is plus 1. That's feasible. You can create such a species. Okay, so I'm going to stop here. And again, I will see you soon with another lecture. Thank you very much.